Okay, we're looking at 6-4. We're wrapping 6-4 up today. We have one topic, well, one slide of two topics. It's linear speed, angular speed. And then it's all practice problems. Okay? So we practiced yesterday with arc length. Get to where we are. All right, so this was yesterday. We practiced arc length based on the angle of rotation and the radius of the circle. Okay, now we're here. We're looking at linear speed and angular speed. Okay, so listen to the words to know when we're no longer talking about arc length. We're not talking about like how long is the cooked noodle. Had to do it, sorry. We're talking about what? Speed, okay? So think like Lightning McQueen. We're talking about speed here, which means we've moved into like a physics problem. Linear speed, and the name of it, by the way, literally tells you what type of speed it is. Linear speed is the distance traveled per unit of time, okay? And we're talking about in a linear motion. So like a motorcycle, a boat, something floating down the river. I mean, I'm just thinking like it just keeps moving in a horizontal manner. Angular speed means it's rotating. How fast is it rotating? Okay, so like a satellite or a planet or a moon. I'm trying to think of something else, examples. Well, we got plenty coming up. So, or bicycle wheel, or the tire of a vehicle. That's angular speed. The angle, how fast is it moving as it creates an angle? How linear speed, how fast is it moving if it was to leave like a line behind it and you can measure the line? You know, how fast is it moving? We have two formulas here. We have linear speed, angular speed. These two formulas are going to combine on the next slide. Okay? So right here, we're writing them separately. Linear speed in terms of the distance traveled versus how long it took. Angular speed in terms of the rotation it created versus how long it took it to build that rotation. So these are separate concepts. The next slide, they come together in the same formula. Linear speed is written in terms of the angular speed, meaning they've combined them together, okay? So wrap your mind around that. You see three different formulas, but the one where they're combined is the one we're going to use, all right? But I wanted you to understand where it comes from. Okay, so look right here. Let's take a couple notes. Make sure I'm on the right color. Linear speed is the distance traveled per unit of time. For instance, if you had a person walking to get over here, right? The linear speed would describe how fast they move. The distance that they travel from point A to point B would be S, distance traveled. We're kind of used to that because yesterday we had S as that arc created, like the length of the noodle, right? T for time, that's easy to understand. V just represents what you get once you calculate how far they traveled divided by how fast it took them, how long it took them, and that's the linear speed. Yeah. Angular speed is the amount of rotation per unit of time. So like miles per hour is linear speed because you're talking about the distance that you traveled from A to B. That's miles per hour. That's linear speed. But the RPM rotations per minute? Okay, if you ever noticed on your dash, one of the gauges that you never look at is fluctuates quickly whenever you push the gas down. That's your RPMs. That's your rotations per minute. That's your angular speed. That's how many times like it's rotating per 1 minute of time. This little W looking thing, I had to remind myself, omega. I was about to say alpha. That's not alpha. This is omega. It's the lowercase one. You don't have to memorize that. I just wanted you to know it's not a W. It's the Greek letter omega, which is what we use to represent angular speed. It's okay if you don't remember that. Theta is the rotation in radians. This is important. And then, of course, you have your unit of time. Let's make a note right here. For example, a bike wheel or bicycle wheel, a bike wheel has angular speed of, and this is just a random example, 150 revolutions per minute. That means as 1 minute of time passes, the wheel will have rotated 150 times. That's what that means. Those are the only notes to take on this slide. So this is just showing you the formula concepts separately. Now they're going to merge together in the same equation, and they're going to give us this right here. If you're one to highlight, you might want to highlight that this is the linear speed in terms of angular speed. We're using both. And this right here is the formula you need. And you don't have to write this, but I'm going to put, we'll use this for practice. Linear speed is the point, a distance from, like r, from the center of the rotation, travels, and then angular speed, this is really important right here, has to be in radians. Angular speed has to be in radians. So if the problem starts in degrees, you have to do work first with that before you go to the formula, okay? So at this point, that is the lesson. Now let's actually put it into practice. And we have
2 slides.
4, 3. We have 5 practice problems. They are dense. There's a lot to think about as you're doing it. Everything is doable. It's just unfamiliar because you normally we're working in algebra. We're not looking at physics problems, okay? You will be given this formula on the exam, and I even tell you that, like that the W stands for the angular speed in radians. So you are given that, okay? It's like I said yesterday. I'm not looking to see can you memorize it. I'm looking to see if you had it in front of you, could you use it and answer the question. All right, so let's practice. An Earth satellite in circular orbit, 1,200 kilometers high, makes 1 complete revolution every 90 minutes. What's its linear speed? They want us to use 6,400 kilometers for the length of the radius of the Earth. So first of all, we do have a picture. Second of all, we have quite a bit of information in here. The little pink title is just a title of the type of word problem. So there's a reason. That's why I didn't read that part. Let's read back through. Let's look at our picture and let's figure out what we're working with here. An Earth satellite in circular orbit, 1,200 kilometers high, makes 1 complete revolution every 90 minutes. So if you look at this picture, and they're telling us that the radius of the Earth is 6,400 kilometers. but the satellite's not sitting on the Earth, right? The satellite is up in outer space. So what is the actual radius? How do I get it? 7,600. How'd you get it?
I added 6,400 to 1,200.
Yeah, so you've got to think from the center of the Earth all the way to the satellite. So we need the Earth's radius plus the distance that the satellite is above the Earth. So I'm actually going to come up here because this is going to get crowded. So I'm going to make a note first. And to help you understand this, I'm going to label every single thing. Okay, you don't have to do that if you don't want to. Like, you know that the radius of the Earth is 6,400, but instead of just writing 6,400, I'm going to write radius of Earth, which is 6,400 kilometers, plus height of satellite. I'm going to label it so you know where it's coming from. When you're working with stuff that's unfamiliar, then be more detailed along the way, and it makes it easier to understand. So the height of the satellite is 1,200 kilometers. Do a quick check to make sure we have the same unit of measurement we did, and we get 7,600 kilometers for what variable? Well, that's you just described the
R.
radius, yeah. So this is R. Now, they don't normally all require that type of little front-loading word. Let's go back and read. It says a satellite is in orbit. We now know that the radius of that orbit is 7,600 kilometers. It says it makes one complete revolution. Your revolutions, your rotations, your angles, all three of those words mean the same thing, need to be in radians. They've just secretly given you the radians. Do you know where they are? We practiced it 2 days ago. What's one complete revolution in radian? 2 pi. If you forget that, then just think to yourself 360. Oh, but wait a minute, I got to be in radians, and then come to 2 pi. So right here, they're giving you the fact that the revolution that we're looking at is 2 pi. Then it says every 90 minutes. What's that? That's our time, right? Our time is 90 minutes. What does it ask us to find? Linear speed. Okay, again, this is unfamiliar, so let's go back and remind ourselves what we're working with here. The formula is V equals R omega. V's velocity, or linear speed. Go ahead and associate those two together. Your linear speed is the velocity at which the car is moving, or whatever. R is the radius. Omega is the angular speed. Okay. Come back over here. They said, what is the linear speed? This means we don't know V. That looks like an R. Let me redraw that. We don't know V. And we no longer need this part about the 6,400 because we've already taken that into account. So I'm going to take some notes as well with what I've got. I don't know V. I do know time is 90 minutes. I know R is 7,600 kilometers. I can already see that I don't know V. There's something else I have not talked about, and that would be omega. We don't know omega right away. I'm going to try and make that look like omega. We don't know omega. So I cannot use, I'm going to come down here. My goal is V equals R omega. I can't use that yet because I don't know omega. So this is where we backtrack 2 slides and pull the formula for omega. Y'all stay with me. Backtrack 2 slides. There's the formula for omega. This is common sense, y'all. Both of these are. It's just one's talking about linear speed, one's talking about angular speed. If you are driving a car, what is your linear speed measured in? Miles per hour. Distance traveled per time, right? Keep that in the back of your mind. Angle rotated per time spent. Distance traveled per time spent. So these are the same concepts. It's just one is when you're talking about measuring out, and then the other is when you're talking about rotating, okay? So while you're unfamiliar with using these things, you've been dealing with miles per hour already as a driver. So that is actually your linear speed. Okay, so we're going to find omega first. We said omega was the angle rotated divided by the time it takes to rotate that. What's our angle of rotation? Look up here. That's our theta, right? Theta would be how much we've rotated. It says we've made 1 complete revolution. So that's 2 pi. How long did it take us to do that? 90 minutes, right? Now, the good news is, in this case, like we just typed in the calculator, type pi as well. So you're going to enter a fraction in there, 2 pi on top, and then 90 on bottom. Be comfortable with the ugly decimals. All of these are ugly. We're going to go to 5 because these are such ugly decimals. We need the most of the number there. So I wrote approximately 0.06981. Now, here's where you've got to remember to keep track of what you were talking about, because when we get to one of the problems where we have to have it in the same unit of measurement, it helps to know what your units were to begin with, right? Okay, so theta was in pi mode, which means that's radians. You with me? Remember, miles per hour, that means what number's on top? Miles per hour. Miles, what's on bottom? Hour. Keep that in mind, right? So come back over here. What was on top? A radian measure. What was on bottom? Time in minutes. So radians per minute. Now you know omega, which means now I can come right here. And what I would do is I would leave that ugly decimal in your calculator and then just pull it down by saying, times the radius. But I am going to show my work right here. The radius was 7,600 kilometers. And I'm pulling down omega, which was this, right? So 7,600 times 0.06981, or that decimal answer. Did you get 530? We're going to go to the nearest whole number on this answer. Yeah, 530.
It would be 531.
Is it? Yeah. Okay. So I'm going to put approximately 531. Now, we need to know what we're talking about, okay? If we're talking about velocity, go back to miles per hour, but we're not in miles, we're in kilometers, we're also not in hours, we're in minutes. So that's your unit of measurement, kilometers per minute. And that's the answer. You're going 531 kilometers per minute. Is the math challenging? Probably not. Is it uncomfortable and unfamiliar? Absolutely. The good news is we only cover this stuff in this section, and then of course you would just need to know how to do it for the exam. And we would practice it beforehand. Now let's try an angular speed. When you unlock it, it will probably, when you pop the door open, it'll probably unlock. Yeah, see it unlocked. All right, angular speed. An anchor is hoisted at a rate of 2 feet per second as the chain is wound around a capstan with a 1.8 yard diameter. What's the angular speed of the capstan? Okay, you gotta know what you're talking about here. It really helps to understand the picture. They gave you a picture. The capstan is that gigantic, what looks like spool.
Oh, that's the thing that anchors on.
Isn't in sewing, isn't that called a spool? I think so. It looks like a gigantic spool, and it's where the metal anchor wraps around to when they're storing it, and then it unwraps when they anchor down. Okay. It says that it is hoisted at a rate of 2 feet per second. If you see the word rate, that means they're already giving you one of the speeds. You've got to think about, am I talking linear or angular? You literally look at the unit of measurement to answer this question. If it's linear, you're going to see like inches, feet, centimeters, kilometers, miles, yards, millimeters. I'm trying to think of all the. You're going to see things like on a ruler or a yardstick. If it's angular speed, you would see degrees or radians. Okay, so make sure to know when you're looking at which one. This is a linear speed, which means velocity. They're giving you the velocity is 2 feet per second. They're giving that to you. Then they tell me that the diameter of the capstan is 1.8 yards. Anywhere in here we talked about diameter? Nope. What do we need? We need the radius. So if the diameter is 1.8 yards, I'm showing all my work here so you know my thought process. Brody, stay with me. Then the radius would be what? 0.9, right? Do we have a problem already? There you go. We've got a problem. We've not even started to answer the question, and I've already written feet per second here, and then over here I've written yards. So look at the two and think about it. If the velocity's in 2 feet per second, I don't want to convert to yards, right? Because that's not even a full yard. 2 feet's not a yard. So I'm going to take the radius and I'm going to take it and write it in terms of feet. So how many feet are in a yard? 3. So I have 0.9 yards. So I'm going to multiply that by 3 feet to get that I'm actually dealing with 2.7 feet. So that's R. R is 2.7 feet. So you got to pay attention to how we got that. That conversion shouldn't be bad. Everybody knows 3 feet in a yard. Always ask yourself, which one's bigger. Yard's bigger, right? And I'm converting it to feet. So I've got to think about that yard had 3 feet in it. So I'm going to multiply by 3 to get it in terms of feet. Now we can actually answer the question. It says, what is the angular speed of the capstan? The angular speed, right? We don't know it. Because they gave me the velocity, the linear speed, and because I know the radius, I can use this formula, right? But what should I do before I go plugging stuff in so it's easier for me? move it around. Do the cup game here. We don't want velocity, we know it. We want angular speed, like this is the goal. This is the one I don't know. So I would move R by division. So, and I'm actually going to flip it because I don't like my variable on the right. So this, I'm going to draw an arrow to say, okay, I'm going to cup game this, shuffle things around. And then now I'm ready to plug stuff in. V, let's remember what I said. Write out your units of measurement because then in the end, it's easier to know what the unit of measurement is. V was 2 feet per second, and R was 2.7 feet. This is also when you would realize, like if you forgot to convert to feet, you would recognize, oh snap, one's yards, one's feet. So go to your calculator and do 2 divided by 2.7. I went to 4 decimal places. Tell me if you get this. Alrighty, stay with me. This stuff is challenging. Did y'all get that? Alright, now we've got to write our unit of measurement. Always go back to what you were trying to find because that's your clue. Your answer should either be in like yards, feet, inches, centimeters, kilometers, millimeters per time, or your answer should be in radians or degrees per time, right? It said to find the angular speed, so I'm talking radians or degrees. Because we've not dealt with degrees at all, it's safe to assume we're in radians. So this would describe the radians per, now what was our time unit? Second, which is why you want to write that so you don't forget it. Now the textbook you leave right there and be like, you got it, you're good.
I feel very confident about this.
Oh yeah. I think we need more practice, especially because we've only converted one time to the same unit of measurement. So go to the next slide. Let's do a Ferris wheel.
Ferris wheel.
I know the next time you go to the fair, you're going to think to yourself, this is that math problem this Holcombe was talking about.
I don't go to the fair, Miss Holcombe.
I take my kids to the fair. I have so many good memories at the fair when I was a kid.
I love the
Yeah.
You know what? It's what you make of it. If you
I went-
go there and walk
I
around
went to-
and like, yeah, that's
I
the
went
one
to-
I grew up going to.
Some fair where they serve barbecue. That's the only thing I do.
I love it.
Did you say the
It's usually one in October is the one we go to because it's not as hot. 'Cause we woo. If I'm hot, I'm done.
A fair?
I'm done.
What?
All right. We have
Always
a
yelling
Ferris-
at me again.
I'm just glad you're awake. We have a Ferris wheel. Has a diameter of 10 meters. It's rotating at a rate of 500 meters per minute. What is the angular velocity in radians per second? I read it once.
736.
I know I'm for the Ferris wheel. Now I'm going to read it again and underline and take notes. A Ferris wheel has a diameter of 10 meters. I don't want that. I need what? I need the radius is 5. I'm going to copy meters. It's rotating at a rate of 500 meters per minute. If you see the word rate, then they're already giving you one of the speeds. You have to know which one they're giving you. The way you answer that is you look at the unit of measurement. Is it linear or is it angular? It's meters. Meters is linear. So right here, rotating at the rate of 500 minutes is giving me the linear speed. What variable are we using for linear speed? V for velocity, right? Then it says to find the angular velocity. So velocity, speed. Find the angular velocity. That's what variable? Omega. So I don't know omega. And then they are actually telling me where they want the answer, what unit of measurement. So we have to keep that in mind. All right. Let's go to what we said we are using. We've got V equals R omega. Let's cup game this. What am I going to move to make it easier for me?
R.
We'll move the R. So I'm going to draw an arrow to say I'm shuffling this, and now I'm going to mirror image it. Omega would be V over R.
So it's 100 meters.
So V is 500. Remember what I said. Write your units of measurement. You need to check the linear part and make sure it matches. We got meters on top. We got meters on bottom. Perfect. What's 500 divided by 5? 100. Now, go back and remind yourself what you were talking about. We're talking about omega. This is how I remember omega is the angular speed. I think of drawing the omega and I'm like, I have to curve, like I think of rotation. So that's how I remember that the W, the omega, is the rotation speed. Okay, so this is angular speed, which means if we've not dealt with degrees, we're in radians. So this is radians per what? Minute. What's the problem, Houston? They want seconds. So you got to think about it this way. If it's 100 radians per 1 minute, change 1 minute to reflect how many seconds are in a minute, and then we have to recalculate.
It's 100
So I'm going to make a note like, this, make a note, drawing an arrow to say, wait a minute, that doesn't matter. I'm just saying, wait a minute, we got a problem, Houston. So 100 radians per 1 minute. I'm not going to write 1 minute. I'm going to write 60 seconds. And you get about 1.67.
Yeah.
And now we're in radians per second.
Easy.
It's really not bad. Like I said, the math's not bad. It's just so uncomfortable because you're just not used. You're not used to doing this. All right. Next one. Your bike has a wheel, diameter of 30 inches. You are traveling and your wheels are rotating at 141 revolutions per minute. What is the bicycle speed in miles per hour? I've read it once. I know I'm talking about a bike. I know I'm talking about the wheels rotating. I'm going to go back and read it again, and I'm going to take notes. Your bike has a wheel diameter of 30 inches. I need the radius, so it would be 15 inches. You're traveling and your wheels are rotating at 141 revolutions per minute. They never said the word rate, but they said per. They said it's doing this per minute. That's a rate, okay? Go back to miles per hour. That's a rate. So they're giving me a rate here. Which one are they giving me? Is it angular speed or linear speed? It's angular because they're talking about how many times it's rotating around in a 1 minute span of time. So the angular speed is 141. I'm just going to write REV, revolutions, turns, per minute, right? Minute per 1 minute. Now, if it involved. If it rotated one time, how many is that in radians? If it rotates one time, that's 2 pi. If it rotates 2 times, 4 pi. It's 141 times. How do I get it?
282 pi.
And how'd you get it?
Multiply.
Multiply. So right here, there's a secret little, like, you gotta remember this. This is how many times it's rotating. I need its actual, like, speed in radians. So I'm gonna multiply by 2 pi to represent the radians for one rotation. It's safe to say you can leave it as pi. Actually, it's not a bad idea. I went to decimal. Why did I do that? I went on to decimal. Let's leave it as pi, and then at the very end we'll type that in. So that would be 282 pi. Now we're in radians per, what was this? Minute.
And then you just multiply that by
Now it does say, what's the bicycle speed in miles per hour? What's the bicycle speed? So that's velocity in miles per hour. They want miles per hour. I'm going to put mph. I was about to write m over hr, but then that would look like meters. mph. You're used to that miles per hour. That's a fraction. Miles is on top, hours on bottom. So don't forget that's a fraction. All right. So we know R. We know omega. We are told to find V. So this is our V equals R omega formula. What's the radius?
15.
15 inches. What's omega?
That 282 pi.
282 pi. And that's radians per minute. So type 15 times 282 pi. I went to the nearest hundredth. Oh, you know what it was? Because I didn't leave it as 280. All right, so what is it?
It's just
0.4.
0.94.
Did you get that? Okay, here's this challenging part. Go back and remember, remind yourself, what was I talking about? What are my units of measurement? And then write it. So I'm talking about like linear speed, miles per hour, feet per second, whatever. This was inches per minute. Did it want that?
No.
Nope.
Okay, so what you listen? What you got to do?
Wait. Hold on. Let me be transparent here. This is when I hate math. I'll be honest. I absolutely can't stand units of measurement.
No, this is fun.
And convert. It is fun.
This is fun.
But it's annoying because it makes me feel stupid because I have to think super hard about it. I have a master's in math, and when you tell me to convert from a unit of measurement to another one, I'm like, wait a minute now, I gotta get my chart. Okay, so we do have to convert. This is a problem. This is inches per minute, and I'm going to make a note. But I'm going to put miles per hour question mark. Like we wanted it in miles per hour. Inches per minute. If I said, how fast were you going? If an officer pulled you over and said, do you know how fast you were going? And you said, I was going 13,000 inches per minute. You might get out of the ticket just for being cute, or you might actually get 2 tickets. I don't know. Don't do that. So I'm going to make a note down here. I'm trying to get to miles per hour, right? Trying to get to miles per hour. How do you do this? I'm really talking to myself here. You write what you're at, okay? I'm at 13,288.94. Now, go ahead and write it as an actual fraction. This was inches per 1 minute, right? I need the goal. The goal is miles per hour. Okay. 1 mile, I'm in inches, right? 1 mile has how many inches in it?
62,360.
Yeah, you're welcome. I gave that to you. I had to look that up. Or not look it up. I had to calculate it. All right. Not equals. So we're going to multiply this. 1 mile has 63,360 inches. If I'm trying to go from inches to miles, I have to cancel out my inches and convert to the mileage, right? So the inches needs to be on the bottom. Like, think about it this way. If I'm talking about a distance that I've traveled, and I'm talking about in inches, then I have a huge number, right? If I was talking about in miles, it should be a smaller number. So if the goal is to go to miles, which should be a smaller number, then that's your indication you're dividing. So that's why I put it on the bottom. So that's why you wouldn't flip those. Because if this is flipped, then I'm going to have an even bigger number, which is your indication something's wrong. You with me? Okay. Now that's going to take care of my miles. I'm going to also go ahead and take care of time. It's in what? Minutes. I need it to be in hours. And hours goes where in your fraction?
On top.
Per, miles per. It'd be in the bottom, right? Yeah? Where would hour go?
Oh, on the bottom. Sorry,
Yeah.
sorry.
Okay, so 60 minutes is 1 hour. Notice how I arranged that. I arranged that by knowing that my final answer should be miles on top, minutes on bottom. Which is how I use my units of measurement here. 1 mile on top, 1 hour on bottom. And now, of course, you would just go to your calculator and type these in. You should come to, I went to the nearest 10. You should come to about 12.6 miles per hour. Double check that you get that.
Yeah.
Now, if I'm being honest, I would say that was the most challenging question. The next one, which you would think is the most challenging because it's the last one, in my opinion, is easier. Let me tell you the answer, and you can try it, okay? So on the next one, Brett and Will are riding a carousel. Do y'all know what a carousel looks like?
Yeah.
Okay, imagine having a drone with a camera flying above the carousel, hovering above, and taking a picture down below. You would have what shape? A circle, right? Okay. Brett always selects a horse on the outside row. Okay, so Brett is somewhere out here. Outside row. Will prefers the road closest to the center, so his would be a smaller circle if it was to rotate around, right? So almost like a bullseye. And that is Will. I'm going to make a note. I don't want to draw them side by side. I'm going to draw Will right here. These rows are 19 feet 3 inches and 13 feet 11 inches from the center respectively. Respectively means that based on who they talked about first goes with the number first. Based on who they talked about second goes to the second number. So Will is 19 feet 3 inches. So I'm going to make a note. RB is 19 feet 3 inches. Will is how far? 13 feet, 11 inches. I did RW, RB, so I would know like which one's which. You're going to basically calculate the linear speed for both people and then find the difference between them. Your answer is 0.92 miles per hour, which is telling you that depending on where you sit on a carousel, you are traveling at a different speed. So if you're looking for more speed, you would sit further away from the center, right? Because you've got to travel faster.